Today we're going to talk about the non-inertial frame. Non-inertial frame. How do we calculate the movement of object inside the non-inertial frame? Let's assume this. First of all, we have inertial frame, stationary frame with I direction, J direction, origin point O. Inside that inertial frame, we have an observer, for example, here try to observe something. And somewhere inside that frame, we have a triangle box and sitting on top of some surface. And that box itself is moving with acceleration a0. So we can assume there's another frame called the inertial frame. For example, we have inertial frame and that moving along with exactly the same acceleration a0 in the same direction. Okay, now if we assume there's a cylinder, okay, radius r, mass m, this cylinder is put on top of that triangle box and also moving along with the non-inertial frame at acceleration a0. But the cylinder will have to roll. If we assume that the cylinder will roll along the slant surface without slipping. First of all, roll without slipping to make the calculation simple. Then we also assume this angle is theta. Then our question is, to the observer inside ROJ, stationary or inertial frame, if I only look at the center of mass of that cylinder, then we'll say what is the acceleration of that center of mass? That's the question. And we know that the center of mass is inside the non-inertial frame that moving at acceleration a0 already along with the triangular box. At the same time, it will roll without slipping along the slant surface. So if we assume that within that non-inertial frame for another observer, for example, another observer and fully attached to that triangular box, sitting inside that box. For that observer, this observer 1, this observer 2, he will see that the cylinder is rolling along the slanted surface. And let's assume that observer in that frame will observe the cylinder center of mass, okay, rolling along the surface. We call it A1, A center of mass 1. If that's something we can find out, then we can conclude that for observer 1 inside the stationary box, the A center of mass of that cylinder is that cylinder is doing two things. First of all, it's moving relative to the stationary frame at acceleration 0. Secondly, it also moving with an acceleration a1 relative to the non-inertial frame that is observed by observer 2. So all we need to find out is what is a1 inside the non-inertial frame. Okay. In order to do that, first let's do a free body diagram that can be observed by the second observer inside non-inertial frame, which is moving with a0. So let's do that. We have slant surface of that box, right? We have angle theta here. This is the cylinder. So first the cylinder would have gravity mg, and it will have, since it's a contact the slant surface, you will have a normal force in this direction. Additionally, since the slanted surface or the box is moving to the left, so to observer 2, that travel along with this accelerating frame, it will see an opposite force. Means every object inside that frame will see a force in the opposite direction of a0. The force is called F prime, equal to what? Suppose equal to m a0 in magnitude. This is due to the equivalence principle proposed by Einstein. Einstein thought in a very deep space, if you are sitting in a big box without knowing outside, and your box is propelled by a rocket in the accelerating upwards very fast, for example, with acceleration g, then you will see all the apples inside that box will start falling to the floor of that box, almost like dragged down by gravity. And this is the equivalence principle between a non-inertial frame in the deep space with respect to gravity. So that means anything inside the accelerating frame will equivalently experience a force in the opposite direction in magnitude equal to ma. So this is why we're using this. So the acceleration frame going to the left with acceleration a0. So object inside the frame, when we observe them, and we're going to the right, and the force magnitude equal to m a0. So since we have force pulling the cylinder upwards, then the cylinder will have a friction force going against that trend of moving upwards. So the friction force will going downwards. That would be called F friction. So effectively we have 4 force acting on the cylinder, but all other 3, N, F prime, and mg going through the central mass. So with respect to central mass, and there's no rotation caused by those 3 forces, but the friction force did not go through the central mass, so you'll create a torque, and that torque will make this cylinder rotate clockwise, upwards. So based on that understanding, now let's write down some of the basic Newton's equations. So first of all, let's decompose all the forces into two directions. One is this direction perpendicular to the surface. Another direction is parallel to the surface. And you know this angle is theta. Also for the another force here, the equivalence force, so we have one in this direction, another in this direction. Again, so you can prove this is also theta. So let's write down all the equations. First equation is along the vertical perpendicular direction here, we have n should equal to mg cosine theta plus we have f here, f prime and sine theta. That's along the vertical direction. Second equation should be along the parallel direction with respect to the slime surface. In that case, the center of mass is moving with acceleration acm1 upwards. So we should say ma1 equal to what? That equal to the total net force. First of all is f prime and cosine theta, and minus and mg and sine theta, and minus f. Now we need to find out what ff. Ff is a frequent force that causes the rotation. So in order to cause the rotation, and we have another rotational law, means the torque caused by this force is ff times r and equals to I times alpha 1. Alpha 1 in this is a rotational angular acceleration, because the rotation of the cylinder is rolling without slipping. So the angular acceleration is related to the linear acceleration. Linear acceleration A should equal to R times angular acceleration. That's the condition for rolling without slipping. If we plug that in, we can find F equal to, besides, we have to say I equal to mr squared times 2. Okay, that's known. So if we plug that in, we should get F equal to 2m over 2 and A1. Then we plug this into equation 2. Then we get ma1 plus A1 equal to f prime cosine theta minus mg sine theta. So that just means A1 equal to 2 over 3. And let's plug f prime into this. F prime is ma0, so this should be a0 cosine theta minus g sine theta. This is the acceleration of center of mass in the non-inertial frame and observed by the second observer there. Now if we go back to the original one, then we can say, okay, the center mass respect to the first observer or initial frame should equal to A0 plus A1. And since this is I, this is J, this is O, so this is A0 and this is A1, and this is the slant surface of theta. So we can continue on this and decompose A1 to ij direction. So we have A0 and I, but it's in the next direction, plus A1 cosine theta, I direction, plus A1 sine theta in j direction. So that should give us A1 cosine theta minus A0 in the I direction, plus A1 sine theta in the j direction. So this is the center mass acceleration. Okay, repeat again, A1 cosine theta minus A0 I plus A1 sine theta j. This is our conclusion.